Good afternoon. This is our second video lesson for the Earth History class, spring of 2021. This is chapter 2, Earth Materials. Okay, so this is a pretty quick chapter to cover, although it's pretty important. It's a very quick lesson on what you need to know about minerals and the different groups of rocks. Now, to be fair, sedimentary rocks are very important in Earth history, but we are going to cover them in more detail later on in, I think it's chapter 6. So this is just a brief snippet of each type of earth material, enough to try to help us understand plate tectonics and some of the later chapters that we will discuss. All right, so we are going to begin with mineral classes. So there are more mineral classes than I have on the board. These are the only ones we really need to talk about for this class. Okay, so we'll begin with native elements. These are minerals that contain just one element. So examples would be things like diamonds, graphite, gold, silver, platinum, sulfur, that kind of stuff. Not too many of those. Then we have sulfides, which are going to consist of metal and sulfur, and examples here would be pyrite, FeS2, iron sulfide, fool's gold, or galena, PbS, which is lead sulfide. Because of COVID, we're not going to be sending samples around this semester at all, which is a shame, but it's a safe thing to do. So I may hold them up at the front for you guys to take a look at. And certainly when we get to some of the fossils, I'll probably just have some set up front at my table and maybe hold them up in the air as we talk about them, and then invite people to come closer and get a look at them before or after class. All right, back to mineral classes. Sulfates are going to include metal, sulfur, and oxygen. And a good example of this would be gypsum, which is calcium sulfate, CaSO2, I believe, with some water in the crystal lattice. Oxides are going to consist of metal and oxygen. Examples here would be things like corundum, which is where rubies and sapphires come from. Then we have the carbonates, and they're going to be important because they're going to make up limestones. It turns out that not only are many limestones out there fossiliferous, the limestones definitely help us figure out a lot about what has happened in Earth's history before we had humans here to document everything. Of course, as long as we've had humans, we haven't necessarily had documentation all that long. So the carbonates are going to consist of a metal, like say calcium or magnesium, and the carbonate anion, which is CO3 with a -2 charge. So a great example of carbonates would be, well, limestone, which is calcium carbonate, CaCO3. All of these mineral classes here on the left-hand side of the board, what we've talked about so far, are non-silicates. I need to point that out. All right, now we're going to move over here, and we are going to move on with our mineral classes, and we're going to talk about silicates. Okay, so the silicates are a class of minerals, and it's going to consist of some kind of metal and something we refer to as the silicate tetrahedra, which is SiO4 with a -4 charge, and then that symbol I have drawn there that looks kind of like the triangle on the Citgo gas station. That is the symbol that we use to try and show an individual silicate tetrahedra. Each of the three corners is an oxygen atom. Where the dashed lines in the middle come together is the fourth oxygen atom, and then we are assuming that there is a smaller silica in the middle, and we can just make a triangle and put our dashed lines there from each corner meeting in the middle, silicate tetrahedra. Now, silicates are so important. They're definitely the most abundant mineral class on Earth, and they're making up 95% of Earth's crust. They're also abundant in the asthenosphere and the mantle. So with the exception of the inner core and outer core, the majority of our planet is made up of the silicate minerals. Now, there are many classes of silicate minerals. And if you took earth science, either with me or somebody else, or even at a different school, you likely had to learn the classes of silicates. We are going to let that go for this semester. We have 4.57 billion years of Earth history to cover in one semester. 19 chapters. We're not going to worry about the different classes of silicates. If you remember them from a previous class, then that's awesome. All right, let's scoot on over here. So still working on silicates here in the blue. The silicates are in the blue marker. I need to get some more markers. It's amazing how long they just don't last. Okay, so we're going to break our silicates down. Even though we're not going to look at the individual classes, we're going to break them down into two main groups. We're going to have ferromagnesian versus non-ferromagnesian. Okay, so the ferromagnesian silicate minerals, we can also refer to those as mafic. That's what's in parentheses there. And what does that mean? It means they are containing iron and or magnesium. And the oceanic crust is made up of these ferromagnesian silicate minerals in the form of mostly basalt but some gabbro at depth. Okay, so then the other group, non-ferromagnesian minerals, we're going to refer to these as felsic. So this is our other group of silicate minerals. They're not going to have any iron and magnesium. All right. They are going to have metal, with the exception of quartz. Quartz has no metal, but other than that, all the silicates that are going to have metal, and the ones that are non-ferromagnesian, while they're going to have metal, it will not be iron and magnesium. So our continental crust, which is going to be granite, and I'm looking over at something I wrote for later. Okay. Yeah, anyway, our continental crust, which is mostly granite, is made up of non-ferromagnesian minerals. All right. Now we're moving to the black marker again, and we're going to do a quick snippet of igneous rocks. So igneous rocks, so where do they come from? Well, they're forming from molten rock, okay? And that molten rock is described either as magma or lava, okay? If it's below ground, it's magma. If it's at the surface, it's lava. And a good way to remember that is magma chamber, lava flow. Where is the magma chamber? It's below ground. Where's the lava flow? It's at the surface. Something that Kilauea volcano often does, as well as Mount Etna on the island of Sicily. I think Sicily's part of Italy. I could be wrong. Okay, so there are two groups of igneous rocks, intrusive and extrusive, so that's where we're going next. So again, if any of you have had an earth science class before, you have a leg up for the first 3 chapters. And if you've not had earth science before, and that's okay, it's not a requirement, don't worry, you'll get caught up. And we're only doing a brief snippet of some of the material that we did in earth science. Okay, so intrusive versus extrusive rocks may sound quite familiar to some of you. Intrusive rocks form in the subsurface below ground from magma, and that magma is going to cool very, very slowly, allowing the crystals to grow large. Okay, so a good example of an intrusive igneous rock would be granite, which is also felsic, non-ferromagnesian type of igneous rock, making up the continental crust. Okay, I'm going to have to move to carry on with our notes. All right, so where are we going next? Extrusive igneous rocks, up at the top there in the middle, in the black marker. Extrusive igneous rocks form either at the surface, on the surface, or very close to the surface, perhaps in a very shallow intrusion. And extrusive rocks are cooling from lava, and they're cooling much quicker than you would have in the subsurface. Therefore, the crystals are going to be quite tiny. Okay, so a good example of an extrusive igneous rock would be basalt. We're going to see that basalt is going to make up our 3 most shallow intrusions here. And that's where we're going next, igneous intrusions. So again, this could be a review for some of you. If not, it's not hard to learn. We're going to take a quick look at 5 basic intrusions. Number 1 is the igneous dike. So it's a tabular intrusion. Tabular means like a tablet, so like an iPad kind of shape, or just a notebook. Okay, that kind of shape. It's not going to look like a chimney or a column, even though when you see these things on the side of the road, as I've drawn them here, it might look like that. Okay, so it's tabular, it cuts perpendicular to layers, and it tends to be basalt. So in our drawing here, well, let's talk about our abbreviations. SS stands for sandstone. LS stands for, you guessed it, limestone. SEDS is just short for sediments. We expect in most places to have sediments on top. Not always. And then shale is just shale. So what you see here is basalt cutting perpendicular to the layers. That's important, is that this tabular intrusion here cuts perpendicular to the layers, tends to be made of basalt. Just know that that basalt is a tablet running, imagine it running back into the wall there. All right, next we have, I need to put this camera on my shoulder, it's getting heavy already. Okay, next we have the igneous sill. So these are also tabular intrusions, meaning like a tablet, like an iPad or a tablet of paper, but it's going to cut parallel to layers. So what you see here in our drawing, you see sediments on top, you see a couple layers of shale, and then you see a horizontal basalt intrusion that has cut in between shale layers and is parallel to the layers. That is an igneous sill. And of course, again, that is tabular in nature. All right, now we're going to get to our two bigger intrusions. The pluton is a bulbous, very large, well, large, really a blob-shaped intrusion. Meaning it doesn't necessarily have a shape other than a blob, like a big thing of pizza dough, maybe. Bulbous. All right, and the plutons, they tend to be granite. They could also be diorite. I'm not sure that you'll see much diorite in this class. We're going to go with granite. So you see there we have some layers in the background, as we did with our dike and sill. And then you have this magma that intruded, this large magma body that intruded up into those layers. And it's just kind of round. Now I have some dimensions on here regarding the width of plutons. They can be meters across. That should say meters. You know what? I'm going to scoot up here and just erase the M. All right. Oh, shoot, I meant to erase the K. Now we got to walk back over here and get a marker. That is okay. We're trying to make a point here for the size of the pluton. And why is that important? Because it's going to be smaller than the batholith. Let me get lid on that marker. All right, back to where we were. Okay, that's better. The size or width across of our plutons could be a few meters if they're really small, or it could be tens of kilometers across. They can be pretty big. I went on a field trip years ago. We took some students from UNCP to the Pageland Pluton. I think we actually might have crossed down into South Carolina to visit that Pluton. And it was big, but it wasn't huge. All right, moving again. Okay, now we're gonna discuss our largest intrusion, which is called the batholith. These are very large, super huge, immense, and they are also blob-shaped, but in a linear fashion, meaning that they can be quite long. Okay, so I have a good example of a batholith. It's called the Sierra Nevada Mountains in California. Okay, as a matter of fact, geologists, we don't necessarily refer to it as the Sierra Nevada Mountains. We're going to refer to it as the Sierra Nevada batholith, because that's what it is. It's okay to call them mountains. Nothing wrong with that. I think the skiers in California probably are just going to call those mountains. So in our drawing here, you see some layers of rock and sediment in the background, and then you have this larger granite intrusion that is punched up into that rock. And then we have some dimensions here for scale. This one could be, you know, hundreds of kilometers in width. So I think the Sierra Nevada batholith, oh shoot, I knew that was going to happen. So in the classroom, if you don't move or you stay in one half of the classroom, the light goes off and I have to walk over by the door to get it to come back on. Yeah, we'll do this all semester long. Anyway, the Sierra Nevada batholith is a good 100 kilometers across. Meaning if you're on the California side and you want to get to, say, oh, I don't know, what's on the other side of there? Nevada. Yeah, that's like 100 kilometers of width across. How long is the Sierra Nevada mountains, batholith? Hundreds of kilometers in length, and that just depends on the length of the subduction zone that formed it. What is a subduction zone? We will learn that soon. Some of you might remember from earth science. Number 5, I'll save for last. It's the weird one. Now this tends to be a smaller intrusion, kind of like the sills and dikes, and it's basalt as well, and it tends to be a more shallow intrusion like the sills and dikes, but it has a blister shape. We're going to call it the laccolith. So I have a crude drawing there, the best I could do, of a blister-shaped intrusion that is basalt and pretty close to the surface, punching up into the rock layers that are already there. All right, for this last one, I'm going to have to scoot down the hallway here. We have a whole nother set of boards to go. Okay. Yeah, this could be a 30-minute thing. It'll take forever to upload to YouTube. So we're still in our igneous rocks, and now in the orange marker, we're going to take a look at some terms we use to describe magma types and the igneous rocks that they form. All right, we're going to begin with felsic. These are, it's a magma that's going to contain mostly light-colored minerals, like say quartz and feldspar, muscovite, minerals that are less dense than the mafic counterparts. So examples of rock types that come from felsic magma would be granite and rhyolite. And granite is making up the continental crust. Then we're going to skip to the kind of the opposite end, which is mafic. Mafic magma is going to consist of mostly the dark colored minerals, things like augite, hornblende, maybe some maybe a little bit of olivine. Anyway, so these dark colored minerals also tend to be more dense. So examples of rock types that come from mafic magma are going to be basalt and gabbro. And basalt, mostly basalt, a little bit of gabbro, are making up the oceanic crust. So it's fair to say that oceanic material is more dense than continental material, and that's going to make sense when we talk about convergent boundaries when we get to chapter 3 and which type of material is going to lose the battle. We'll get to that in our next video lesson. Okay, number 3, intermediate magma. An intermediate magma is roughly about half felsic and half mafic minerals, and the rock types that come from that are diorite, which can also make some plutons or batholiths, and then andesite. Andesite is an extrusive variety of the intermediate rock. Andesite is named for a famous mountain range. Did you guys guess what it is? The Andes in South America. Okay, number 4, our fourth and final type of magma is called ultramafic. Okay, so ultramafic magma would have mostly just olivine and augite melted in it. And these are our most dense of the silicate minerals. Now, this type of magma no longer erupts at Earth's surface. We will not see an ultramafic magma flow in person or on Discovery Channel because it just doesn't happen anymore. Now, we know for a fact that this magma used to erupt at Earth's surface long, long ago when Earth was a younger planet and hotter, meaning that we had more internal heat. And we know this because of greenstone belts. We will get into greenstone belts eventually, maybe like chapter 8. All right, let's move on to our next board. I have to admit that I'm always happy to get chapters 1 and 2 over with in this class because everything after those chapters is more interesting, more fun. Okay, I'm gonna have to experiment with my camera angle to try and not have the glare. And no, there's nothing I can do with the windows. They're as good as they're gonna get with the shades. Okay, I think this will do for what's on the far left. Okay, now a very quick snippet on sedimentary rocks. They're so important to Earth history. So we'll look at them in a little more detail in a later chapter. For now, this is what we're going to say about sedimentary rocks. I'm just going to call them sed rocks for short. Sedimentary rocks form from the lithification of sediments. Seds is short for sediments. And this is generally going to require compaction, meaning that these materials get buried and the particles get squeezed closer together, and some kind of natural cement that comes through, like a quartz or a calcite. Sediments that are going to make our sedimentary rocks, sediments form from, well, most of our sediments are going to form from the weathering of some pre-existing rock. That pre-existing rock could either be igneous, metamorphic, or sedimentary, and it can form sediments pretty easily. Sediments also will form from the remains of living creatures, like sea creatures, or the growth of minerals from water, surface water or groundwater. Okay, so sediments are going to form, but they and then they're going to erode, which means that they fall out of the rock that they were weathered out of. But they tend to not just stay where they land. They tend to get moved around, transported by rivers and streams or ice. And then they're going to get deposited. The sediments might move quite far from the rock that formed them. They might move from the mountains all the way down to the sea and form beach sand, or they might make their way to braided streams on the mountainside and not go much further. Now, eventually, the sediments may lithify into rock, meaning that they would compact and have a natural cement lithification, and lithify into rock. Just to give you an example that time alone is not enough, okay? When I was in grad school at UNCW, and I was working on a research project, and we were looking at sediments along the Cape Fear River, and we were looking in, was it Bladen County? Anyway, some of the units that we were looking at were anywhere from 65 to 70 million years old, and were still sediments, and all that time they never become solid rock. Okay, again, we're going to have to move around and get the glare away from the middle of this board. Okay, so 3 groups of sedimentary rocks. Number 1, clastic or detrital. Those 2 terms mean the same thing. These are sedimentary rocks that form from pieces of pre-existing rock. Common examples are sandstone, siltstone, and shale. Number 2, we have biochemical. These sedimentary rocks are going to form from the remains of once living organisms, shellfish, or plants. Examples of rocks that these produce would be limestones, chalk, which is a limestone, and coal. Moving around again, and we'll have to try to keep the glare. Oh, Lordy. All right, maybe if I can, no, that's no good. How about right there? Okay. Number 3, third type or group of sedimentary rock, chemical sedimentary rocks. These form from aqueous solutions, groundwater or surface water. In the case of surface water, we might refer to those sedimentary rocks as evaporites, so they are comprised of evaporite minerals. Some examples here would be halite, which is the mineral name basically for salt, sodium chloride. If it's in rock form, we call it rock salt, I should say. And then gypsum is another example of a chemical sedimentary rock. All right, I am going to give my right hand a rest from holding this camera and try to finish up this chapter. All right, we're gonna do some purple ink. Okay, I think the glare is off of the purple. Okay, so this is our very quick and dirty lesson on metamorphic rocks. Okay, so metamorphic rocks form by the alteration or changing of some pre-existing rock. This is mainly accomplished through heat and pressure, but there's a couple other agents of metamorphism that may or may not be present. Every metamorphic rock has a protolith or a parent rock, the rock it used to be. Here are some common examples. Marble, which makes beautiful countertops, used to be limestone, basically recrystallized limestone. Quartzite used to be sandstone. It's basically recrystallized sandstone. Slate, which is a very pretty rock and useful for all kinds of things like chalkboards. Slate used to be shale, And then gneiss. The G is silent here. Gneiss, not gneiss. Gneiss could have had at least a couple different parent rocks, granite or shale. All right, I'm going to try to not have that plastic shield in between my camera and our notes. Okay, last bit of notes here for chapter 2. The agents of metamorphism, meaning the things that are acting on that rock, changing it. Heat, and you have increasing heat with depth. Pressure, you have increasing pressure with depth. Heat and pressure are enough to do it. Hydrothermal fluids just refers to heated groundwater, may or may not be present. And if you have volcanic activity nearby, you are very likely going to have hydrothermal fluids. And then differential stress, which just means pushing or pulling unequally in different directions. We're not going to mess with differential stress in this class at all. We're not really going to talk a whole lot about metamorphic rocks in this class. That's why it's super short, half of a board. All right, 2 scales of metamorphism. We're going to have contact metamorphism versus regional metamorphism. Contact metamorphism is small scale, very localized, maybe close to the surface due to an igneous intrusion. So those igneous intrusions that we looked at earlier, and we may walk over and look at those again, are going to cause contact metamorphism. Regional metamorphism is on a very large scale, and it's due to mountain building events, as in collisional boundaries. It could be ocean to continent subduction. It can happen in ocean to ocean subduction and continent to continent collision. Okay, so to give you an example, the Himalaya mountains, which in more recent millions of years, we consider that to be continent to continent collision, there's a whole lot of metamorphic rock there. Okay, so most of the volume of metamorphic rocks on Earth's surface are due to regional metamorphism, not contact metamorphism. Let's walk back over. I'm going to take a marker and add one little thing. We're going to walk back over here to one of our drawings.